This conference will now be recorded.
All right, so we're looking at the transformation of function notes. I told you that I would do this on a video, and then we would talk about it briefly in class on Tuesday before we start reviewing for the exam. So when we were in class together, we talked about how there were 5 major functions that you had to know the shape of. We said that constant and lines, which is the identity function, we wouldn't really be doing much with those since you can graph those using y equals mx plus b. But for things that are a little bit differently shaped, we do want to have some techniques for graphing them if they have a certain format. So you need to be familiar with the absolute value function, which is f of x equals absolute value of x. And notice that it reports in a V shape with the what we call parent or toolkit function being centered at 0, 0. Because whatever you plug into the absolute value, it gives you the positive back of that number. Then I don't know why this picture from the book didn't have this, but by the way, parabolas go on forever just like the absolute values do, so there should be arrows on that. But another shape you need to be familiar with is the quadratic, which is f of x equals x squared. So if there's nothing but an x squared there, it's centered at the origin again, 0, 0. And notice they didn't make up any of the points here. The points that are plotted are all points that are, when you plug them in, what do you get when you square it? So if you square -2, you get 4. You square +2, you get 4. -1 squared is 1. 1 squared is 1. 0 squared is 0. So that is the quadratic shape, the U shape. Okay, the other 3 that we have to be familiar with is the cubic function. And this is when you cube something. So notice that if you cube a negative, it's going to stay negative. If you cube a positive, it's going to stay positive. So it kind of almost looks like a parabola that got split upside, halfway down and halfway up. But it's cubing. So if we do -2 cubed, we're going to be down at -8. If we do +2 cubed, we're going to be at +8. And then the square root function, which we've seen before in the class. The square root of x, notice that they picked perfect squares for plugging in for x. And if it's just square root of x, it starts at 0, 0. You can't plug in any negatives in because you'll get a math and the square root. But square root of 1 is 1, square root of 4 is 2. So that's how they got these 3 points. And then cubed root, which means you have a cubed root instead of a square root, you can plug negatives into a cube root, like cubed root of -8 is -2. So for this scenario, notice it's almost the same values, except we are taking the cubed root of them. So notice I call this walk like an Egyptian. It goes up curved, and then it goes down curved, okay? So those are the 5 main shapes. Now, what we're going to be doing with these is we're going to say, first thing we do when we graph by transformations is that you look at the function you're given and you say, okay, what shape should this function have? Then you want to determine how did they change it from the original cubed root of x or x squared. So there's a couple different types of changes that we're going to see in functions. One is called a vertical shift. This is when they take the function, so like square root of x or x squared, and they add a constant to the end or subtract a constant. If the constant added is positive, notice the whole graph will shift up 1. So notice point by point, this all just shifted up 1 value. If you subtract 1 from the function, then you'll shift down. So a positive k at the end means we're going to go up. A negative k at the end means we're going to go down. And the key to this is noticing that this is outside of the function. It's something that's been added or subtracted after the original function. Another type of shift that we can do is shifting right or left. And notice the structure of this is a little bit different. Notice that this is happening not outside of the function, but inside of the function. It's in the parentheses. So this is a little different because anything that happens outside of the function, you do exactly what you see. So if you see like a +2 after the function, it's up 2. If you see, a ×2 in front of a function, you times everything by 2. If something happens inside the function, we do the opposite of what we see. So since this is actually minus at h, we do the opposite. We will shift to the right. So if you have a function where you have a minus inside with your x, that means you're going to shift the graph to the right. If you have a function where they add something inside to the x, then you're going to shift left. So notice this has a +1 inside. You can barely see that plus symbol there. So they shifted the whole graph to the left one. So that's the difference between vertical and horizontal shifting. Another type of easy transformation is called a reflection. So if you put a negative in front of your function, like if you put negative x squared, where the negative is not part of the part you're squaring, then that's called a vertical reflection. In other words, you flip yourself over the x-axis. The reason it's over the x-axis is because when you're above the x-axis, your y's are positive. When you're below the x-axis, your y's are negative. So it's changing the sign of y. So notice I've got a picture down here. The original function is this dark blue one. A vertical reflection down here is when the negative is outside of the function. So notice it flips it upside down over the x-axis. If for some reason the negative is inside the function, in other words, inside with the x in front of it, then it's going to be a horizontal reflection. It reflects over around the y-axis. Because if you change your x sign, you're changing from being a positive x to being a negative x over here. So notice it flips it this direction. And it says, notice that the vertical reflection produces a new graph that is a mirror image across the x-axis. And then the horizontal reflection, which is the one where the negative is inside, produces one that is a mirror image about the y-axis. Okay, and then the last type of transformations, because essentially we're just going to practice graphing some transformations next, are stretches and compressions. There's two different types. There's vertical ones and there's horizontal ones. So we're going to talk about how do you know the difference between which ones you have, and essentially it's where is it located? Is it outside the function or inside the function? So it says when we multiply a function by a positive constant, we get a function whose graph is sketched or compressed or stretched or compressed vertically in relation to the original function. So if your constant in front, so they're saying if the number in front of f of x, so notice this is outside of f of x, if this is greater than 1, you're going to stretch, okay? If the number in front of the function, like they put 0.5, but that's really 1/2. If it's between 0 and 1, so they're calling that kind of a, then it's going to be what we call a compression. In other words, if I double all my y values, my thing is going to get tall. If I cut all the y values in half, it's going to get shorter. So that's what we mean by vertical stretch and vertical compression. And notice this is double the height. This is half the original height. So here are the general rules for that. So if your function looks like this, with a constant in front of f of x, then if a is greater than 1, it'll be stretched vertically by that factor. In other words, you'll just take all your y values and multiply them by whatever the number is. If it's between 0 and 1, same thing, except it's compressed instead of stretched, and you just multiply all your y values by that factor. If a is less than 0, that means if a is negative, that means there's two transformations. There's either a stretch or compression based on what the number is, and there's a vertical reflection because of the negative sign. So just be aware that if it's a negative number up front, that means you have two transformations at the same time. All right, and then the last type, like I said, is still stretches and compressions, but they're horizontal. So these are things that happen inside the function. And remember, anything that happens inside the function is the opposite of what you think. So notice here's x squared. If you put a 2, so if that's greater than 1, if the number in front is greater than 1, you actually do the opposite. So you cut the whole thing's x's in half, because remember, this is changing x. Anything outside the function is changing y. So notice the x values shrunk to a smaller interval by half. And if the number inside here is between 0 and 1, we're going to call this number b, then you do the opposite. So think about this being 1/2. So the opposite of that would be we would double all x's. So times by 2. So notice that made this have a wider stretch. So this is called a horizontal stretch because you're making your whole graph wider. This is called a horizontal compression because you're making the graph skinnier or narrower. And then this is the formula. So the b is inside the function this time, not outside. If the b is greater than 1, then you compress horizontally by the reciprocal of that. So if it's 2, it'd be 1/2. If it's 3, it'd be 1/3. If between 0 and 1, then you're stretching horizontally by that reciprocal. And then if it's negative, you also have a horizontal reflection. Okay, so here's the rules about combining transformations, and then the rest of this is just working through some examples. So it says when combining transformations, you should follow the specific guidelines here that's kind of like order of operations. So anything that happens inside the function should happen first, specifically anything connected to x. So performing horizontal stretches or compressions, since those are numbers times x, and any reflections over the y-axis, which is if your x has a negative in front of it. That should be done first if they exist. Then you want to do any horizontal shifting, which means was there something added or subtracted to the x inside the function. The next thing you want to do is to perform vertical stretches and compressions and reflections over the x-axis if they exist. That has to do with, is there a number outside of the function times it, or a negative sign times it. And then the last thing is usually to perform the vertical shifting if it exists in your function. So for this first part of this, we're not actually graphing anything yet. We're just going to explain what the transformations are. And notice I didn't give you a specific function. We just don't want to focus on that. We want to focus on what are the transformations. So notice inside here, I see a -1 inside there with my x. So the first transformation that I see is that this would be shifted, and it's opposite to what we see. So instead of left, it's actually right 1. Okay, the second transformation that I see is that outside of the function, there's a ×3. When it's outside the function, it's exactly what you think. So that's making it bigger. So this would be a vertical stretch, since it happened outside, of a factor of 3. Okay, let's look at this one. Now I could write that as a complete sentence if I wanted, but right now we're just pinpointing out the transformations. So there is a shift inside here, and it's a +4, so that means we're actually going to go left. So we're going to have shifted left 4. And oops, sorry, that was supposed to be a number 1 up there. And a 2. Second step would be there's a negative in front of the function. So that means reflected over the x-axis. Okay, let's look at C. The first transformation here is, notice we have a 1/2 times our x. Anything that happens inside, you do the opposite of what you think. So it's actually going to be a 2/1. It's going to be the reciprocal. So that would be a horizontal stretch, because it's actually going to make it bigger, of 2, because you do the reciprocal there. And then this is nothing in front of there. This is a vertical shift, and it's exactly what we think when it's outside. So it's vertical shift down 3. Okay. And then for the last function, we have a negative inside with our x, which means we're reflected over the y-axis. And we have a 1/3 in front. Anything in front, you do exactly what you see. So that's actually a vertical compression, because it's going to make it smaller, of 1/3. Or excuse me, yeah, 1/3. So the only time we flip it is if it's a number inside with x. Okay, so those are something like that will show up on the test where you'll have to describe what the transformations are. Now we're getting down to the nitty-gritty. It says sketch the graphs of f. Make sure to use any use of symmetry, shifting, stretching, compressing, or reflecting. So for this first one here, you need to know the parent graph that goes with this. This is absolute value of x. So over here, kind of remember what that shape was. Absolute value of x, if I put in 0, it's 0. If I put in 1, I get 1. If I put in -1, I get 1, because it's the absolute value of it. And remember, it had a V shape. So these are the 3 points that I'm going to try to shift based on what this tells me. There's a -1 after the function. See, this is the function. So that means we're going to shift the whole graph down 1. Okay, so 0, 0 is going to move to 0, -1. -1, +1 is going to move down to -1, 0. And 1, 1 is going to move down to 1, 0. So notice it is still the same absolute value shape, not drawn very well, but it has been shifted down 1 on the graph. Okay, let's look at a different function. This one is the cubed function, because notice there's a 3 characteristic for the exponent. That means this was originally x cubed. So x cubed also has 0 being 0. If you cube a 1, it's a 1. If you cube -1, it's -1. This is, remember, the one where it has kind of the parabola shape, but it's split. So it's curved up and curved down. So we're going to be moving these points. So this is saying that it's a negative inside the function. Notice it's before we cube it. So that means it's a horizontal shift, and we do the opposite of what we think. So -2 actually means right 2. So 0, 0 moves right 2. This was the point 1, 1, so find that here, move it right 2. This was the point -1, -1. Move it right 2. And then draw the same shape. So there is x minus 2 cubed. All right, this is the square root of -x. So square root of x, we have to know what that shape is. This is why the shapes are so important. If you don't know your shapes, you really don't know how to do this. This is really based on shape of the function and how do you transform it. So if there's a square root of x, just the basic square root of x, square root of 0 is 0, square root of 1 is 1, and then remember you can't plug any negatives in, so you have to do square root of 4, which is 2. So remember this is that half of a parabola on its side. So this is saying that this is a negative inside the function. Notice it's under the radical. So that means we're going to reflect over the y-axis. That means you're going to flip the whole graph across horizontally. So 0, 0 is already on the y-axis. You can't flip something over the y-axis if it's on the y-axis. 1, 1 will flip to -1, 1. And 4, 2 will flip across to -4, 2. So notice it just changes all the x's from positive to negative, but it does not change the y values. Okay, this is 1/4 of x squared, so we need to know what x squared looks like. So x squared, if you square 0, it's 0. If you square 1, it's 1. If you square -1, it's also 1, but it's an x squared, which means it's a U shape. And again, I'm only looking for 3 points, so if you know your 3 points and you know your shape, then you're good. So this is 1/4 of x squared. So remember, if you have a number in front of the function, it's not inside the function because they didn't put it in parentheses. This means that this is a vertical compression of 1/4. Now what that means is that your y values are cut in fourth. Okay, because if it's outside, you're affecting y values. If this had been inside, we would have done the reciprocal and we would have affected the x. So if you think about these as ordered pairs, this is 1, 1, -1, 1, and 0, 0. You're going to cut each of the y values in fourth. That means times it by a fourth. And then the 0. So 1/4 of 0 is still 0. So still at 0, 0. 1 1/4 is really tiny. -1 1/4 is also tiny. So notice this has compressed that parabola so that it doesn't grow as fast. Okay, let's look at E. F of x equals the cubed root of 2x. So notice this is happening inside, which means we're going to do opposite of what we see. So we're actually going to be doing half of the x's, which means that is a horizontal compression. Okay, so let's first of all remember what cubed root of x looks like. That's walk like an Egyptian. 0 cubed rooted is 0, 1 cubed root is 1, and then -1 cubed root is -1. A lot of people want to draw x cubed here. Remember, this is the cubed root, so it actually goes like you're doing walk like an Egyptian, like your hands are going side to side. So we're taking, let's write down these points. So 1, 1, -1, 1, 0, 0. We're taking half of those x values. So that means we'll have 1/2 1, 0 would still be 0, and -1/2 1. So 1/2 1, 0, 0, -1/2 1. So notice it has been horizontally compressed. The x's are closer together than they were before. Still looks like the same graph, but there's that subtle difference that the x's are closer together than they were. Okay, and then the last ones that are kind of in this packet, essentially, is that we want to talk about combining transformations together. So notice this is squared, so that means this is based off of a parabola. So we'll draw our basic picture for parabola, 0, 0, -1, 1, and 1, 1. Remember, that's just plugging those numbers into the function and figuring out the y value. This means that we're going to be doing left 3, and that is going to be done first because it is the closest thing to x. And this means up 1. So you kind of want to draw kind of a picture before you get over to the graph. So I'm going to draw left 3. So take each of these points and move them left 3. So 0, 0 is going to go to -3, 0 because it's moving to the left 3, 2, 3. 1, 1 is going to move 1, 2, 3. -1, 1 is also going to move over 3. So this is just left 3. Then we're going to move everything up 1. So now I can kind of go over here. So we're at -3, 0. We're going to move up 1. We were at -2, 1. We're going to move up 1. We were at -4, 1. We're going to move up 1. And hopefully you will have a better tool than I have right now to draw lines and curves, because mine are all looking pretty messy. But so you kind of have to have an in-between step to help you find that right location. Okay, so let's look at G. This is a square root of x, so we need to draw that toolkit function. 0, 0, 1, 1, and 4, 2. That's what it generally looks like. Okay, so this is actually 2 transformations in 1. So we need to double the y's because it's happening outside the function, because that's a vertical stretch. I'm going to do that first. We then need to reflect over the x-axis because of the negative on the outside. I'll do that second. And then we need to move the whole graph up 5 because of the vertical shift that's after the function. So let's draw some in-between pictures. So you might want to write your ordered pairs here so you can double your y values. So if we double 0, it's still going to be 0. So this is transformation 1. If we double 1, it'll be a 2 because I'm only focusing on the y value. If we double 2, that's going to be at 4. So there we are. So you notice it is stretched upward. Then we're going to take those 3 new points and we're going to reflect them across the x-axis. 0, 0 is already on the x-axis, so it won't change. We're not going to move the x, but we're going to move the y down to the reflection, which would be -2. And then the next point needs to reflect down at -4. So notice same shape, but upside down. And then I'm going to move the whole graph up 5. So start from this point and move it up 5. So up 1, 2, 3, 4, 5. This is the point 1, -2. So go there and go 1, 2, 3, 4, 5. And then 4, -4. Go up 1, 2, 3, 4, 5. And draw the shape. Okay, so that kind of ends what I said was the main part of what you needed to know for the test. There is a question on the test about symmetry. I'm going to talk to you about what even and odd means and if you're going on to trig, you do need to know this, but we don't actually test you on even or odd, we just test you about symmetry. So it's kind of involved in this conversation. The lucky thing is this is really just kind of a picture you look at and you tell me some information about it. So let's talk about this. If a function is symmetric about the y-axis, which means if you find a point on the graph, there is a matching point on the other side of the y-axis for every single point. So that folds completely across that y-axis and matches. Those are actually what we call even functions. Their x's can be different, but they give the same y. So 2 and -2 give us the same y value. There's another type of symmetry which we care about here, which is called origin symmetry. And that is when you have what's called an odd function. In origin symmetry, a point on one side of the graph will have a matching point where if you've changed all of the signs. So in other words, -1 to -1. So for this, notice that you would say, okay, 1, 1 was on this side of the graph. So if I change both of those, they'd be negatives, and that needs to be on the other side of the graph. The way this actually works is that it was flipped twice. It was flipped across the y-axis and then flipped upside down. So that's what origin symmetry is. It's odd function. The other one that is not even or odd is the x-axis symmetry, just so you know what this is. X-axis symmetry means your graph has a fold across the x-axis. In other words, the x value is the same, but the y might be positive on one side, but negative on the other. So you get matches across there. So that's called x-axis symmetry. X-axis symmetry is not even a function, so it can't be an even or odd function because this fails the vertical line test. But it is a type of symmetry. There's some functions that are not even or odd at all. They're just like a line or other functions. And then there's also there's only one function that is both even and odd at the same time, and that is y = 0. In other words, a horizontal line at the x-axis. If you wanted to test for even and odd, and I am going to go through this in the video, but mainly I just want you to know how to pick out the symmetries. but this is helpful if you are going on to farther classes. So even functions say that if the x is a different sign, it doesn't matter. It still gives us the same y value overall. So the way you prove it is you plug in a negative x for all of your x's in your function, and you work it out and say, what would this sign be? What would this sign be? And it comes back out as the original function. If it stays the same as the original function, it is an even function. If you plug a negative into a function and you get the opposite of the original function, that's when you're an odd function. So if you want to determine if something's even, odd, or neither, and from a picture, you can just tell me which symmetry it has. This has y-axis symmetry because it folds beautifully and matches across the y-axis, which means this would be an even function. This one has none of the symmetries we learned. This does not fold nicely across the y-axis. It does not match equally. There's extra stuff. It does not fold across the x-axis and match. Imagine folding the paper over. It doesn't match, which is not even or odd anyways, and it doesn't fold over the origin. If I had an origin symmetry, this point would exist down here, but both negative. So this has none of the symmetries that we need. And that means it is neither even or odd, nor odd. All right, the last picture one. This one's kind of interesting. Notice this point up here is positive, positive, and there's a matching negative, negative down here. So this is a double fold. This got folded once and then flipped upside down. So this is what we call an odd function because it has origin symmetry. Now, if I did give you a picture like this has x-axis symmetry, but in terms of functions, it's not even a function. So it's not even a function. So it can't be even or odd, but it does have a symmetry. Okay, so just to show you how to do this in case you're moving on, like I said, the main part you should focus on in this video for the test was the transformations. But if you want to prove to someone that a function is even or odd and you don't have the picture, you would work out what we call the even and odd test. So the first thing is you put a negative x in for all of the x's. And we talk about how an absolute value of a negative x is the same thing as the absolute value of the positive x inside. So we can actually swap that just by the definition of absolute value. So since that is the original function, that means that this function is definitely even. Okay, so it checks off the even test. The odd test says that you have to put in a negative x for all the x's again, which means this is still absolute value of x. But to check for odd, you have to factor out a -1, because remember, it was negative f of x to be odd. If you factor out a -1, that's going to make that a negative, and then absolute value of x, and then a +3. This right here is not the original function inside there. So this is how you test for odd. Once you've worked it out, you pull out a -1. If the original function is not inside the parentheses, then that is not going to be an odd, so it fails that test. Here's a quick way to note this. If all your powers are odd, you're going to pass the odd test, but not the even test. If you have all powers that are even, like 4 and 2, it's going to pass the even test, but not the odd test. If you have a mix, like a 2 and a 1, that's an even and an odd, you're not going to pass either test. So those are just quick little tricks there. So if I put in a negative x here, that'd be 7 times negative x to the 5th minus 4 times negative x to the 3rd. I would say that a negative to the 5th power is actually going to come out as an overall negative. Same thing for a third, so that changes that to a +4. This is not the original function. So that means it's not even. So even test fails. For the odd test, you do the same thing. So essentially, you can just write this, which is what we got when we plug in all those negatives, and you take it one step further to test for odd. You pull out a -1. And that changes the inside back to the original. So the part inside here, so this is a -1 times f of x, essentially. So that means it passes the odd test. And then very last one, this one is neither even or odd. I already told you that ahead of time, but I'll prove it to you. My pen just froze. Hang on just a second. Maybe I will. There we go. So I'm doing the even test first. If we put in negatives for all of the different x's, notice that this gives me a negative squared is going to be a positive, so that's actually just going to stay 3x squared. But this is a negative to the first power, so it's going to multiply and give me a positive 5x. So notice that is not the original function because that 5x changed signs. So it fails the even test. For the odd test, we write that same guy we just got, which was 3x squared plus 5x plus 1, and then we factor out -1, which changes everything to negatives, and that is also not -1 times the original function, because the original function only had a negative on the 5, not the 3 and the 1. So this one fails both tests. This would be what we call neither. So like I said, I'm not going to count the even odd homework against you guys. If you want to try it, you can, but I'm going to essentially just X that one out when I go to do grades for this unit. Do spend the time memorizing the 5 shapes for transformation and then working on those different types of transformations. On our class, we will sit down together and we will do a few more of these transformations before we review for the test on Tuesday. So have a good night and I'll see you this week.